Hi. So I'd like to explain a little more in depth about how to do the worksheet. So this is the driven oscillations worksheet. So starting with the theory part, they just ask a bunch of questions about the theory behind the experiment. So yeah, I think this is kind of straightforward. So I think if you read the lab manual on this part, it should be pretty clear. But yeah. And this part as well is in the lab manual, the procedure. But yeah, so I think the main thing that I want to talk about though is this data analysis part. So this what you're going to be doing is taking the data from the spreadsheet that was given. So I think that's this, right? So this is the data that we give you guys. And what you got to do is you got to fill out this table here. So there's actually not enough rows in this table. So don't think that there's only 4 rows, because there's actually supposed to be 15 rows. So you're gonna have to add some more rows in what you submit. So just to go through this first column, I guess. So I guess just in general for this table, you're actually going to be using this data down here. So this is the resonancy frequency data. So this natural frequency data is not used to fill out this table. So this table is this second table in the spreadsheet. So so you can actually kind of fill it out in here and then transfer it to your submission if you want, or either way. But these columns correspond to the columns over here. Oh, maybe, yeah, wait, 1, 2, 3. Yeah. So I guess to figure out this first column, the t's, all you have to do is, divide this column by 5. So whatever is in this box will be 18.5 divided by 5. And do that for all of these numbers. So this is going to be the period of the oscillation. So it's how long did it take the mass to go up and down 1 time. So this is how long it took to go up and down 5 times, but you really want only 1 period. So that's why you divide these by 5. Okay, so moving on to the second column. This is the omega. So this is the driving frequency. So you want to figure out at what frequency was the motor running and pushing this spring mass system up and down. And to do that, all you have to do is do 1 over this column, so 1 over t. So for example, so say 18.5, I don't know, divided by 5 will give you some, maybe about 4, I don't know, but say that t is 4. So the driving frequency would be 1 over 4 seconds. So that's the measure of frequency, but they're actually asking for this in units of radians per second. So you're going to have to multiply this 1 over t by 2 pi. So in the end, this should be, if this guy is 4 4 seconds, you should get 1 over 4 seconds times 2 pi. So the 2 pi is on the numerator and the 4 seconds is in the denominator. You get 2 pi divided by 4 seconds. And in that similar way, you can go through each of these rows and fill out this omega column. So moving on to this amplitude, I think this is actually just these. So you can just copy these numbers over into your table. So this is how much distance did the mass go up and down? Yeah. And this last column over here is A divided by A naught. So A is referring to this column. So how much did the mass go up and down? And A naught is actually referring to how much did the motor push the spring up and down. So you call this the so this A naught over here is the driving amplitude, I think. So A is the response amplitude. So this is how much does the spring go up and down, but A naught is how much does the motor push the spring. So what they're asking you to do here is just take the numbers. For example, if you got like a 5 centimeters here, you would just do 5 centimeters divided by A naught would go here. And your value for A naught is given in the table. So it's this 1.6 centimeters. Right, so that's so if this is 5, this would be 5 divided by 1.6. Okay, yeah, so you gotta do this for all of these trials. So you're gonna have 15 rows. Yeah. Okay, so that's that. Then you're gonna have to graph it. So this is the part that I wanted to talk about. So I got some demonstration data here. So let's graph this data. So this is so scatter. All right, so this will be so I should say that the numbers that you're going to be graphing are actually this column on the y-axis and this column on the x-axis. So if you go here, you're going to be graphing this column on the y-axis and this column on the x-axis. So you want to know for a certain driving frequency, so a certain motor speed, how much does the spring mass go up and down? And that's, so you want to make this into a graph. So you take these two columns and graph them like this. So right here, this is demonstration data, but I have this driving frequency here. So this corresponds to this column and this response amplitude here. Right, and the response amplitude is how much the spring mass goes up and down. So, and if we graph it, like you'll get something like this. You're gonna want to label these guys whatever you think is appropriate. But the thing that's kind of tricky is the plotting the fit. So usually we've been doing this linear fit. So before we would do this, we would go like fit linear like that with the right click. But this time we're going to be fitting a kind of like a bell shape rather than a line. So to do this, you hit, if you're on Windows, this would be Control Y on the keyboard. Or if you're on Mac, it's Command Y. If you're on Linux, I have no idea. It's probably Control Y. But so I'm gonna hit Command and then press Y, and it should open up this window. So next you want to go to user define. So this is all to fit this curvy line. So just follow along. So user define. And what we're doing is we're kind of creating our own fit curve. So the linear line fit is built into Cy-Davis, but this, the squiggly one that we want is not built in. So we have to kind of give it to Cy-Davis. So let's call our fit something that we can remember. So we call it driven oscillation, maybe. And then I think you can click down here. And so you leave the parameters the same, but then you go to the lab manual and they got this. So this is chapter 15 near the end, this graphing and analysis. And they have this formula here. So you just copy that. So you highlight it, copy, and then you paste it in here. Like so. Okay, so now you have that. So this is what you want it to look like. And then I think you're gonna just hit save here. So you want to make sure that you save this so it's stored inside Davis. Okay. Now you got that. Then I think you have to click this fit with selected user function. And then I think you hit fit here. See if that works. So you see, oh, maybe. So you can see that nothing has happened yet to the graph, but that's just because we haven't finished it yet. So what this is when you do a fit, Cy-Davis needs some help. So it's going to ask you, what are your guesses for how this fit should look? And you can tell it these guesses by giving it these initial guesses in terms of A and B. So A is here and B is here. And what A and B are actually corresponding to are the, so A corresponds to the natural frequency. So at what frequency is the response amplitude the greatest? So that would be at what frequency is this peak located at? So you're just going to put in something like, so I say, oh, it's about 5. So I double click into this A box and just hit 5, enter. And then for B, I think 1 is okay. Yeah, I think I tried it and 1 was fine. So I'm going to hit fit now and we'll see if it works. So, okay, so it looks like it worked. We got some kind of fit. So I'm going to close this window here and that's that. So you give this a title and axis titles. And I should mention that you know how you usually get like the slope information from the linear fit in this upper box here. But this time it's giving you what it found for A and B. So A, again, A is the frequency corresponding to the peak of this function, or the red line. So A corresponds to the natural frequency or the resonant frequency. So it looks like we have a resonant frequency of about 5 radians per second. And B is actually the damping term. So it's how much did the water damp the motion of the spring. But this is the important one, is this A, I think. So it also gives you the uncertainty for this value. So you can use all this information to try to do the worksheet. And you should put a screenshot of what you get with the correct title and axes and the fit shown as well. And yeah. So that's how you do that part. I think the conclusion and the virtual experiment are very similar. So I'll let you try to do these on your own. Um, but yeah, so good luck.